Good morning to ya. Welcome to the Unit 3 Derivatives, okay, review notes. Okay, this is for my AP Calculus AB review course, as I like to say it. Okay, we are not going over every single little tidbit of Unit 3. We are going over the meat and potatoes of the important stuff for derivatives. I'm excited about this unit because to me this is where calculus really starts and takes off. Unit 2 was on limits and continuity, and that is important to understand, where derivatives come from. Okay, but to me, derivatives is really the start of this, upper echelon of mathematics that we call calculus. All right, so I'm psyched. Let's get right into it. Boom. All right. First of all, let's talk about the definition of a derivative. This, my friends, is how we use limits to come up with a derivative. All right. Now, remember, this is just notation, and we'll talk about that in a second. F prime of x, the derivative of f of x, is equivalent to the limit of f of x plus h minus f of x all over h as h approaches 0. Now, if we go back to solving limits, we realize that we always try to throw this number into this variable. The problem with that is, okay, I cannot throw a 0 into the denominator, okay? Because if I throw a 0 into the denominator, my expression, okay, my rational expression, my fraction becomes undefined. And some black hole somewhere in the cosmos spits out some star, and weird things happen when we try and divide by 0. Okay, so what I will do here is if I have f of x equals x squared plus 3, okay, let's call it 2x squared plus 3. I know based on my rules that the derivative of this, and we'll cover our rules in a moment, would be 4x, okay? But I'm not going to use my rules. I'm actually going to use the definition of a derivative to solve for this derivative, okay? So I know 2x squared plus 3 is my function. I know the derivative of that should be 4x, but I'm now going to use my limit here to come up with that 4x. Now, because I know my shortcut rules, I know my answer should be 4x. Okay, when I'm done doing my work here for this thing, I should come up with 4x. All right. Now, what I love doing as a teacher is before we learn the shortcut rules to just get this answer, I still have kids use this. And I'll look at my equation here, and I'll say, yeah, you should come up with 4x. And kids, not knowing the shortcut rules, will tell me, like, man, mister, how do you do that so fast, man? And then in my unit, it's Unit 3, Day 3, I go over the rules, and the kids just look at me sideways, and they're like, I hate you so much, mister. And they don't understand why we got to learn this first to get there, but it gives you a better understanding of derivatives. Okay? So let's get started. I'm going to take x plus h, and I'm going to throw that into here, f of x plus h. So anywhere there's an x, I'm going to substitute in x plus h. So I've got 2 times x plus h squared plus 3. All right? Now, I'm going to subtract the original equation, the entire equation. Do not write it like this, minus 2x squared plus 3. Because right now I'm only subtracting 2x squared. I am not subtracting 3. I always want to subtract the entire function. Okay? That is all over h. And if I do this right, I really should always write the limits as h approaches 0. I still cannot throw 0 in for h here. So what I'm going to do is I'm going to FOIL this. Okay? And if I do that right, I get 2 x plus h times x plus h is not x squared plus h squared. I literally need to take x plus h and FOIL it. These two and combine like terms. If I do that, I get x squared plus 2xh plus h squared. Okay. I still have my plus 3. Don't forget that. Okay. Now, I'm going to distribute my minus sign, okay? Minus 2x squared minus 3 all over. We still have my h here. All right. So there's really one more thing I can do on the top, and that's distribute my 2 in that blue color. All right. So I'm going to distribute this to each one of these 3 terms. And I should have as follows. 2x squared plus 4xh plus 2h squared. Still have my plus 3. Okay. I have minus 2x squared minus 3 all over h. And let's not forget, I really should be writing this every step of the way. So the limit is h goes to 0. At this point, the way I teach it, 2 things should always happen. Okay? 2 things should always happen. Anything in my numerator that does not have an h should cancel, which means anything from my original function here, and it transferred to here, anything without an h here should cancel. Okay? So let's take a look at that. I have a negative 2x squared and a positive 2x squared. Okay, those should cancel. Boing, boing. And I also have a minus 3 and a plus 3. Ooh, look at me. Gone, gone. Everything left has an h. Okay, so I said 2 things should happen. Everything without an h should cancel, and it did. And the second thing is everything left should have an h. And why is that cool for us? Because now I can take an h out of every term. An h from this term, one of these 2 h's, this becomes a 1, and this one is gone. Now I don't have a denominator anymore. I will go this way. I have 4x plus 2h. And let's not forget that's a limit as h goes to 0. Now I can plug an h in here because there's no denominator. Okay, 4x plus 2, my h is 0. Anything times 0? And I just end up with 4x, which is what I said we should end up with anyways. Okay? Oh, I love teaching Unit 3, Day 3, and explaining to kids the shortcuts. And they say, all this work I did, and this wasn't a bad one, was unnecessary. No, it was necessary. It was just a lot more work. Okay? And speaking of notation and derivatives, these here are just all different ways you might see a test or a calculus book or a professor display derivatives. Meaning, if I have an equation y equals something, y prime means the derivative of y. Likewise, if I see f of x function equals something, blah, 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 f prime of x means the derivative of f of x. Okay? If I have y equals, they might not always use this, although that's the short way to do it, and mathematicians really like to do things quicker, okay, mathematically speaking. You might see dy dx. That means the derivative of y. Okay? And likewise, if I see f of x equals d over dx, this is not multiplication. This means the derivative with respect to x of the function f of x. Okay? There you go. It's just all notation. So let's talk about where differentiability or derivatives don't exist on a graph, even though the function is continuous. All right, so graphically speaking, if I see a corner, a cusp, or a vertical tangent line, okay, these 3 things listed here, okay, it is continuous, but the derivative does not exist, means it's not differentiable, okay? A corner is a graph that goes da-da-da-da-da, ba-da-ba-da-ba. It's a point, okay? And I'm going to go back and talk about, I did a 3rd video for the review notes for Unit 2. And in that video, okay, I said that derivatives graphically are a lot like limits. It has to be the same values. I'm coming from the left side and the right side, okay? The derivative as I approach this way, this point, this corner, that's a negative derivative, obviously. It's not the same as I approach this way, which is a positive, okay? So therefore, the derivative isn't the same from both sides, so I can't take the derivative of a corner. But it's continuous, right? I can draw that without picking up my pencil, okay? A cusp is like a squeezed corner. It's like almost like a cursive V, okay? Same deal. The derivative is not the same from both sides. A vertical tangent line. That's if I'm drawing a graph here, blah, 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 and something comes straight up like that, all right? Let me explain why this vertical tangent line here is continuous. That's the easy part. I can draw it without picking up my pencil, but it's not differentiable. I can't take the derivative there. Let's go back to something simpler. What is the derivative of a horizontal tangent line, of a horizontal line? The derivative is 0. This is going back to algebra, okay, algebra 1. The derivative of a vertical line is undefined, okay? And derivative is the same thing as slope, okay? So the slope of a horizontal line is 0. The slope of a vertical line is undefined. This is a vertical line, so the slope is undefined. If the slope is undefined, the derivative is also undefined. In this class, when I teach, okay, whether it's pre-calculus and we talk about calculus, if it's AP Calculus AB or this review course, I always say one thing all the time. Derivative is the same thing as slope. Slope, it's the same thing as derivative, okay? They're synonymous, all right? We cannot take the derivative of a vertical tangent line because it is an undefined slope or an undefined derivative. All right. Now this time, anytime something is discontinuous, I hope you know you can't take the derivative. Okay. Okay. Vertical, not vertical tangent line, vertical asymptote. Can't take the derivative there. Where a graph jumps. Okay. I can't take the derivative there. A hole in the graph. I cannot take the derivative there. Anything that creates discontinuity, you can't take the derivative of. This is really important to know. If a function is differentiable, it must be continuous. Meaning, if I can take the derivative, it has to be continuous. Okay, something like this. Okay, this is continuous, so I can take the derivative anywhere. The derivative right here almost looks like it's 0. I'll use m because m is slope in a lot of equations. Y equals mx plus b. That's slope, so I'll use that derivative. The slope here, or derivative, is 0. Since it has a derivative, it's continuous. I don't know, the slope here might be, I don't know, 1. Okay, the slope here might be 4. Okay, any place I can take the derivative, it is continuous. That's a rule. The reverse is not always true. How can something be continuous but not differentiable? Well, we just went over 3 of them. Corner, cusp, vertical tangent line. Okay? Corner, cusp, vertical tangent line. Ooh, fantastic. Sorry, that was my Mad Hatter impersonation. I had to throw it out there at some point, and now you heard it. Okay, 1336 into this video, mark it. Now, there you go. Simple. Calculator. Oh, calculator. The calculator can take derivatives, but only if they give you an x value to plug into the derivative to get a number. It cannot take the derivative implicitly, meaning if I say, give me the derivative of x squared, okay, if I say f of x is x squared, what's the derivative of f when x is 4? Well, I know the derivative of x squared is 2x at x equals 4. So I know that's 2 times 4, which is 8. Okay, that's good. The calculator can do this because I have a value for x. The calculator cannot say, okay, if I say give me the derivative of x squared, the calculator cannot give you this. At least the calculator that we use, a TI-84, this one right here. By the way, the 84 does not do that. Okay, so no. Calculator can't do that. The calculator can do this. Yes, ding, smiley face. Less work for me, yay. So let's take the example I just did. If I go to math, and I have it highlighted up here, now I do math, and then I pick number 8, which is n deriv. That's the derivative function in the calculator. Turn it on. Oh, let's move this way. Ah, yep, okay, jumps. It jumps, people. Don't be alarmed, it just jumped. Okay? Turn this on, hit enter, and I go to math. And I scroll down here, and I'm going to pick number 8. See, it says n deriv right there. Right here. Bang, bang, bang. And I hit enter. Look at this me. Remember our function was d over dx of some f of x? That was one of our notations. I have to put an x there. And I put my actual equation. In this case, it's x squared. And now I need to put what the value of x is. Well, when x is 4. All right? And if I hit enter, I get 8. Beautiful. Glory be. Awesome. It's a great thing to have. Derivative rules. These rules right here, these 4 basic ones, and we'll get into a few more, but let's start with our 4 basic derivative rules. This is how I knew that my x squared, I don't know, what was it, plus 3, was 2x. Or excuse me, it was 2x squared plus 3 was 4x. This makes the definition of a derivative obsolete in terms of calculating and figuring out derivatives. The only way you are going to have to use that definition of a derivative, that f of x plus h minus f of x all over h, the limit as h goes to 0. The only time you got to use that is when they tell you to specifically use the definition of a derivative to find the derivative or whatever. Okay, so right now, let's go over these basic rules. Now, the derivative of a constant, okay, it's always 0. Boom. Okay, so if I have f of x equals 7, what's f prime of x? Guess what? It's 0 because 7 is a constant. Okay, the derivative of negative 13, 0. The derivative of pi is a constant. It is 0. Any value that does not have a variable that is a number only, the derivative of that will always, always, always be 0. All right? Let's take a look at the basic power rule. This one is money. I love it. Okay. Let's say I have some number m. M is a number. Times x raised to some n value. N is also a number. M and n are numbers. Okay. What I do is, okay, if this is f of x, f prime of x tells me I take my n and bring it out front and multiply it times m. My x remains the same. And then whenever n was up here, I simply subtract 1 from it. That's it. So for example, if I have f of x equals 3x to the 5th, all right? I take my 5, I bring it down front and multiply it times my 3x to the 5th, but I subtract 1 from that exponent. So I end up with 15x to the 4th is the derivative. Okay, simple enough. All right. Now we have the product rule and the quotient rule. All right, the product rule and the quotient rule. Okay, let's say, now product rule doesn't mean I'm multiplying some constant times an x. That's not the product rule. I mean, that means if I'm multiplying 2 functions, like x squared plus 3 times 5x cubed plus 7, okay? These are 2 equations, so to speak, all right? Let's say I have some function u, and I'm multiplying it times some function v. These are not constants, they're functions, okay? Let's say f of x, sorry, didn't leave myself enough room. So f of x equals some function u times some function v. The derivative of that would be the first. That's the first function. The first times the derivative, we'll call v as our second function, times the derivative, that's what this d means, the derivative of the second, plus the second, just as it is, times the derivative of the first. Okay, so in terms of notation, I would take the first one, which is u, just as it is, times the derivative of the second. The derivative of v would be v prime, plus the second, which is v, just as it is, times the derivative of the first, which is u prime. All right? That's what that is. First times derivative of the second, plus second times the derivative of the first. All right, so let me give you an example. F of x equals x squared plus 3 times 5x cubed plus 4. Okay, this will be my first one. This will be my second one. The derivative of my function x is the first, x squared plus 3, times the derivative of the second. Okay, now I'm going to use the power rule for this one here. That's going to be 15x squared. And then the constant rule, the derivative of any constant is 0. So that's it. First times derivative of the second, plus the second, just as it is, 5x cubed plus 4, times the derivative of the first. Okay, the derivative of x squared, again, I'm going to use my power rule. That becomes 2x. And the derivative of my constant is 0, so it's nothing. So there you go. This, all right, that right there is the derivative of f of x. Mister, do I got to simplify it? If they just tell you, if this is a short answer, and they tell you to find the derivative of f of x, you're fine. If this is multiple choice, your 4 or 5 answers might not be like that. They might combine, like distribute and combine like terms. All right? If they want to know the derivative, if they gave you this, find the derivative at x equals 2, I mean, why would I combine all this stuff? I'll just put a 2 in for all these x's, turn them into numbers, and then do the math. That's much easier. There's less likely chance that you make a mistake. Okay? All right, now the last one here, the quotient rule. And there is a little rhyme I use for this one. Boom. A little too high. Quotient rule. If f of x has two functions, u divided by v, this is what we do. It is a little rhyme here. It is low d high minus high d low. I draw a line and I square below. You see how that rhymed? Low d high minus high d low. Draw a line and square below. Now, I'll explain this in a minute. If I were to switch this, if I were to put high d low minus low d high, draw a line and square below, that does not rhyme, so that is wrong. Okay? So what does this mean? That means I'm taking the low, that's LO. My denominator is the low, and I'm multiplying that times the derivative of the high. You know, I didn't do my H in cursive, so why am I doing it in cursive here? My high is the numerator, okay? Minus high, just as it is, times the derivative of the lower one, which is my denominator. I mean, literally, my fraction is high is the numerator, low is the denominator. I draw a line and I square the entire denominator. I square below. So let's use our same u and v. Let's say u was x squared plus 3, and v was 5x cubed plus 4. I'm using the same things I did here for my product rule. All right? So I would take the low just as it is, 5x cubed plus 4, times the derivative of the high. Okay, the derivative of this, we already know that's 2x. We already did that. Minus the high just as it is, x squared plus 3, times the derivative of the low, which we already took. That's 15x squared. I draw a line and I square below. V is the low. 5x plus 4. Don't do that. Ooh, it's 5x cubed. Because that looks like I'm just squaring the 4. I got to square the entire thing. Okay? And that, my friends, is the derivative, the quotient rule of our original function f of x. Okay, given these things for u and v. All right? Product rule and quotient rule are very important. They come into play all year round. All year round. Okay? All these do. But you're good to go. You're super. Okay, we are at the 25-minute mark, so I don't like these to go more than 30 minutes. I try and keep them right around there. So we will finish this problem. We'll stop here, and that will be the end of part 1, and we will pick it up with part 2 of the unit 3, which is derivatives review notes. All right? So find the equation of a line tangent to the curve y equals x squared plus 3 over 2x at the point 1, 2. All right. Anytime we want an equation of a line, okay? This happens to be a tangent line. Equation of a line. You are always programmed to know y equals mx plus b, and that's fine and dandy. But in calculus, there is one that is so much more helpful. It is as follows. Y minus y1 equals m times x plus x1. This might have been introduced to you in algebra, but hardly used, okay? This version that we're going to use is the point slope formula or equation of a line. This one is slope intercept because m is your slope and b is your y-intercept, okay? Everybody knows that. You can use that. It's a little bit more work. You're going to see how easy this one is, okay? This is called point intercept, or excuse me, point slope, because you have a point, an x and a y, and then you have a slope, m, okay? And all we need is a coordinate and our slope. And let's not forget, I said it earlier, slope is the same thing as, okay, m is slope, and that's the same thing as derivative, okay? So if I get a point, I just need my derivative, all right? So let's take a look at this. Okay, equation of a line tangent. First of all, let me explain that. If I have a graph that curves, and they tell me I want the slope of a line tangent right here. A tangent line is something that it touches once. So I'm basically coming up with the equation of this line. That's my tangent line. It's tangent right at this point. Like if this might be an x value of 2, okay? Find the slope of the tangent line when x is 2. That's that right there, okay? They want us to find the equation of a line tangent to, and I don't know what this graph is going to look like, but let's just make something. At the point 1, 2, here's 1, here's 2. At this point, I don't know, I mean, the graph might come through it like, like that, do something crazy like that. They want us to find right at this point the slope of that tangent line. All right? Again, I'm just making something up. I don't know how accurate that graph is. It's not very accurate to what they gave us right here. So, equation of a line. Let's start. First of all, this is nice because they give us an x and a y value. Okay, that's our coordinate. Oh, nice. I need an x and I need a y. So y minus my y value of 2 equals, I still don't know my slope yet. That's the one thing I'm going to have to find out. Times x plus, yeah, I'll be okay. Man, some of you guys that know math could have called me out on that. That's a minus x1. Okay, let's do our highlight right there. Okay, which means that's minus my x value, which is 1. Okay, the only thing I need is my slope. Oh, slope is the same thing as derivative. That means if I take the derivative of y, that would be the same thing as slope, wouldn't it? Nice. All right, I'm going to have to use my quotient rule here. Low d high minus high d low. Draw a line and square below. So I will do this. It is low d high minus high d low. Draw a line and I square below. Okay, I'm leaving space here because I'm going to fill in my values. Okay, it is low, just as it is, 2x, times d high. The derivative of this is actually 2x, minus high, just as it is, x squared plus 3, times d low. The derivative below is 2. Okay, I draw a line and I square the entire below thing here. There you go. That is my derivative. That is my slope. How do I get a number value? Well, I see all these x's here. You know I like to use highlighters. See an x here, an x here, an x here, an x here. If only I had an x to plug in. Oh, wait, I do. Okay, so all I've got to do is throw a 1 into all those x's and simplify it. It's going to give me a number. That's my slope. That's my derivative. All right, so we have 2 times 1, okay, times another 2 times 1 minus 1 squared plus 3 times 2 all over 2 times 1, this whole quantity, squared. I mean, that's very simple. 2 times 1 is 2, times 2 times 1 is 2, 2 times 2 is 4, minus 1 squared is 1 plus 3, that's 4, times 2, that's 8, all over 2 times 1 is 2, 2 squared is 4. All right, 4 minus 8 is negative 4, all over 4, that's negative 1. That is my slope, that is my derivative, that is my m value. Boom, that's your equation of a line, right there. You're welcome. Now, if this is multiple choice, and multiple choice has all their equations listed as y equals, I can just make this y equals, okay? If this was short answer, this is an equation of a line. You are perfectly set and done, okay? If it is multiple choice, sometimes all you got to do is just add the 2. If they say give it to me in y equals form, I don't have to use this. Okay, I don't have to use slope intercept. I could just say y equals negative 1 times x minus 1 plus 2. There it is, y equals form. Let's say it happens to be in this form right here. Guess what? Just, combine things. Distribute the negative 1, then add the 2. So y would equal negative x plus 1 plus 2. So y would equal negative x plus 3. There you go. Slope intercept. Okay? But this, my friends, you know what? Screw that. This, my friends, keep on going back. You're perfect. You're beautiful just the way you are. And we're all done. All right? I will see you for part 2 on the Unit 3 derivatives review notes momentarily. For me, it's going to be like a week till I make the next video. But for you, you're just going to hit play next. And lucky you, you get to like time warp me. That's weird. Don't time warp me.